All right, guys, let's get started. Good morning. So today we're gonna sort of wrap up the default version of the gradient descent with the logistic regression, and then next week we're gonna have a look at a couple of variants for the gradient descent, such as stochastic gradient descent, and on the case of using logistic regression for multi-classes. And then in 2 weeks we're gonna start with the neural networks. So I'll have a quick wrap up of what we talked before in the last session. But first of all, let's just have a quick example on measuring the in-sample error for two distribution of data like x1 tilde and x2 tilde. So with two different methods that we already know. One was linear regression, the other one is logistic regression, and let's see the properties of logistic regression, and how could it help us with this type of situation when linear regression cannot tell us much about the error that we might have in our model. So suppose you have two x's, x tilde 1 with e and 10, and that was for the class that was classified as +1 or a true class, and the other one was like x2 tilde minus e and 10. That was for the class that was classified as -1, and e was defined as 0.001. So you can define, given you have two different x's, so you can define two different lines. So like L1 and L2, depending on the weights you're going to use for those, like W1 and W2. So if you put your first line as L1 equals to x equal to 0, it's as if you have this line, so L1, and these were your +1 and -1, right? So you see that using this in a three-dimensional space, your W would be 0, W1 would be 0, 1, and 0. Also, you can define another line to classify it perfectly for you, and that would be L2, which was x2 equal to 0. So another line like this. I was like 1, x2, right? And also this can classify it good, with no problem. All right, now we're going to see, given our two methods, in-sample error for linear regression and in-sample error for logistic regression, what are the differences between these two? So first of all, if you go for linear regression, linear classification, so we want to classify these 2 points, and L1 and L2, as you see, they have classified them correctly. So for the case of linear classification, the En, which was the indicator function of the Yn, for the case that the output of the sign function W transpose Xn wasn't equal to 1. And on both cases, you see that if you calculate the En of W1 and En and of W2, both cases are going to be 0. As you see, we have good classification in between these 2 points. However, if you apply the logistic regression that I'll present you in the next slide, you're going to see that there is a difference between your in-sample errors on both cases, given your W's. So now we're going to use logistic regression. So the in-sample error of W1, as I talked about it yesterday, we could have calculated with the formula of 1/2 of the log of 1 plus e to the raise of minus w1 transpose x1 plus the same value for the plus cases. So because we were taking into account the both case of y equal to +1 and -1. So now if you compute this, so your x1 t would be, what was that? En 10. So it was En 10 here. And you have your artificial coordinates as 1, x0 equal to 1, and then we want to compute this now. And your w1t would be, so we put L1 as x1 equal to 0, so w1 would be 0, 1, 0. So 0, 1, 0. So if you compute the dot product of these two matrices, so you're going to have 0, you're going to have E, and you're going to have 0 again, right? So the output of this would be E, and you had minus on the case of y minus 1, so that was why this becomes minus E, right? If you compute this, you're going to see it would be for w1t with your x2t, and if you compute these two, you're going to see that, so this one became half the log of 1 plus e to the raise of minus e, and the second one would be the minus of plus e for the x2 transpose. That's why it became minus e, right? And setting your e value here, you would have almost a number like 0.693. 69. And that would be your in-sample error for W1. So let's calculate the same thing for your W2 given our L2 line that we classified. So for L2, if you replicate the same thing, yeah.
Sorry, are you missing a log on the second line?
Yeah, I'm missing a log on the second line. So I'll fix it. Yeah, I'll fix it, and when I upload this slide, I'll fix it. Thanks for that. All right, and then for the W2 in-sample error, so you're going to again compute this. So that would be your W2 transpose would be, from the previous slide we had 001, and you have to calculate both your x1t and also the same thing with x2t on both cases, right? And the output of this would be, the first one would be minus 10. Well, actually, but when you so that was the both case, adding two cases. Yeah, you can do the math, the dot product later at home. So the summation of these two became the log of 1 plus e minus raised to minus 10, which is much smaller than what we found for the in-sample error of W1. So you see that logistic regression sometimes provide us, because of this nonlinearity in its sigmoid function, although it seems pretty normal for the case of binary classification that we had in the previous slide as a linear classification, but here we have different in-sample errors, right? Thus we can say that W2 is clearly preferred over W1 in this case because it has lower in-sample error. So in this case, our W2 was 0, 0, 1, right? All right, now let's see if we had another W. So if we were to consider W2 as 0, 0, 100, what would have happened? It would be still the same line in our 2D space, but definitely calculating the in-sample error would provide the deduction for us that, you know, the loss of in-sample error of the new W2 would be much, much lower. So that's why it's one of the cases that, you know, you can see why regularization is helpful for logistic regression. That's why we had that regularized formula for our in-sample error of W for logistic regression. You're going to see more of these in your tutorial section. I'm not sure if they already covered that or not. Maybe it's going to be in this week tutorial or maybe next week. So you're going to see some samples, some sample questions about it. Okay, so I'm just going to bring a few slides that I talked about last session, just to have a recap on what the gradient descent was, and we finally wrap up with the final algorithm for gradient descent. So as I discussed last session, we knew that in the case of logistic regression, we were having a convex function, so it was providing us with several good properties in order to optimize it, and that's why we could use gradient descent on that, because we could start from any points, and using the gradients, we would end up, you know, in the global minima point or global minimum point of the function, and which was called x star here. So we were discussing that traversing through a function, you're going to have three different scenarios. So first of all, if the point that you were considering in your function was specifically that exact x star, you would have the f prime of x, or the derivative of x, equal to 0, and that would tell you that this point was the minimum, right? So going there. So here, that would be like this point. And the two other points were like the case that you had already passed this one, so the slope was getting towards the uphill one, so the gradient was positive for the case number 2. And the case number 3 would be that you were in this area, your x was, you know, smaller than x star, and that's why your f prime of x would be smaller than 0. So f of x, the function, where it was in a decreasing mode. So using these three simple assumptions, we could apply our gradient descent. But first of all, since the function of f, so I had a question last session from one of your colleagues. So he was asking why we are doing all this gradient descent and also the Taylor series that we're going to discuss in the next slide. And the answer is you don't know what the f is, right? If you knew what f of x was, you would just simply draw it and just visually see the local minima in the case of a 2D case. Or in a higher dimension, you would just get a mean of that function. It would just be a one line of code. But the point is, since you don't know what f of x is, you have to find a way to approximate those points that you are traversing at each step, at each iteration of the gradient descent. When you start from this point, going here, or starting from this point, going this way, right? So at each point, you only have access to the x's, but you don't know what the f of x's are. That's why you use Taylor series in order to expand that. So I talked about it last session as well. So I mentioned that having the correct step size is very important in gradient descent. If you take a smaller step, very small step, it's going to take many more iterations to converge. If you take larger steps, at some point you might just pass your optimal solution, and then that's why we call it you overshooted the optimal point, just like in the case of here. Just like in this case. All right. So the high level view of the gradient descent was first we initialized our x as x0. So in this case, it was here, and then we start seeing that if the f prime of x was 0, that means that we already hit the solution, right? We are already here, so we have to stop. In other cases, on those two other cases, if the f prime of x was greater than 0, so you have to have this deduction, and that was the step size from your x because you've already passed it, so you have to come back. And in the case that it was smaller than 0, you have to add the step size, like from you were here in this case, and you had to add the step size e to go towards better point in your convex function, right? So we mentioned that, yeah, so a smaller step size would slow your progress. Very large step size would overshoot your, solution, and you would pass the solution. You have to come back again. And this would go on in a loop up until you hit the x star, which was your optimal point, the global minima. And also we talked about the number of iteration it needs to converge, and we define it as E of k equal to 1 over k. One of the things that we discussed also was that initially E is large, but when we go step by step further, we make it smaller in order not to overshoot the solution space. All right. Since you've already maybe taken note from these slides, I'm just gonna go a little bit faster on this. If you wanted to have a look at the slides, they were already uploaded here. So So these were here. So as lecture 8, logistic regression. So you can find this slide there. All right. And that was the vector space presentation. We mentioned that we have a unit vector of u that shows the spatial direction for our descent. So when we start from x0 and we are going to up to x1, this u was shown by this direction, and it would show us the direction towards the x star. And I mentioned that u is a unit vector, and the unit vector can be calculated as u divided by the norm of u, and we call it u hat or u itself as a unit vector, right? Okay, I'll pass this again. Again, I described, we don't know what the function f is, but we have 3 different ways to compute the f of j in this case, given x is j, so x of j. And I mentioned that we have 3 different possibilities here, right? Forward difference, backward difference, and center difference. So forward difference was pointing to the situation that you were here at f of j minus 1, and you wanted to go here. That's why you would have to calculate the fj prime, which was equal to fj minus 1 divided by the distance of here to here, and that was delta x1. The backward difference was the case that you were here and you wanted to go backward. That's why you had to compute the fj prime as fj minus fj plus 1, which was this on the function, and a distance of these two, which was wx2. And a center difference was the case that you wanted to go here, you wanted to compute this distance here, and that was why you had to add these two together. And in these 3 different scenarios, we were to use Taylor series approximation, and I brought up the formula that you're going to see again in the next slide. So we were to use this expansion, f of x plus delta x. The reason I'm going fast because you've already had this slide, so you can refer to it. All right, so we could use f of x plus delta x, which could be approximated as f of x plus your first derivatives, delta x f prime x, and then you would go to the second order, delta x 2 factorials multiplied by f double dash x, and then it would go on and on and on. So the more you go further, your error would be smaller, and you had a better approximation, right? So expanding this, we found out that this is the expansion for the gradient descent we should use. So to find f of x1 on a function that we don't know about it, which was the f of x, so we have to find f of x0 plus our step size with the direction that provided us by vector unit, and then the gradient of f of x0 plus the rest of the Taylor series expansion that we weren't going to compute because it was overshooting in our case. We didn't want to spend much time to compute for those smaller approximations. So we call them order of this value, and we put everything else inside that. And through this formula, we could compute the gradient of f of x0 using this. The derivative of f over the derivative of x1 at the point of x0, and that was going on for the whole vector of x. And then finally, the u star, or the optimal direction to go towards your optimal point in your gradient descent convex function, would be calculated as the minimization of u transpose gradient of f of x0, right? So now that we recap the Taylor series and the high-level overview of the gradient descent, let's see what the algorithm actually does. All right. So first we're going to initialize our x0, our starting point. So in different cases, we might need to reinitialize it as well. I'll talk about it in a few slides, that when we do need to reinitialize x0 from different places of our convex function. So for t from 0 up to n, we have to compute the gradient of t as f of xt, and then we need to select the direction. After we computed the gradient, we could use a Taylor series, but we need to have the direction to which way we are going after that, and the direction is minus the gradient, right? Then we have to update the xt plus 1 as our previous x plus the direction we are going with the step size of e, and then we're gonna iterate over until the stopping criteria was found, which was the global minimum, right? Finally, the gradient descent algorithm will return the final value. So we start from any of the point of the graph, the convex function, and we go step by step towards the global minima. All right. Now, let's see 3 different situations that might hinder our stop condition. So 1, in some cases, which fortunately in the case of logistic regression, we don't face it, but in other polynomial functions, you can see it quite enough and also quite often. So you might have multiple stationary points, like you have 3 points here that your gradient was going decrease and increase, decrease and increase again, right? So you had 3 points, first x1 and then x2 and then x3, as the points that your f prime of x would be 0, right? And this would confuse the gradient descent algorithm, because one of them was your global maximum, right? One of them was for local minima, and x3 was your global mean. So in this case, the gradient descent could converge to either x1 and x3, right? Because this would satisfy its conditions. But in practice, we found that in many of the cases, even those local minimas the results are surprisingly good. I mean, it's good enough for our in sample error loss function that sometimes they even consider those locals as the final solution because the algorithm could not step out of that pitfall that was fall into, right? So that was the first case. But as I mentioned in the logistic regression, our convex function help us just to reach to our global minima without any problem because we don't face this type of higher polynomial order. All right, let's see the second remark. How about the saddle points? So in a function such as f of x cubed, so you have x of t, and it's called a saddle point. Also, this point might confuse the gradient descent, right, for its subcondition, because the f prime at this point would be equal to 0 as well, but this is not a global or a local minimum, right? So in this case, with minor modifications, so we can force the gradient descent not to get stuck in the saddle points. So one of the things we can do is like using the second derivatives, because it's going to show that it's going to reveal that this point was a saddle point. And other techniques that it's going to be outside the scope of your course. But one of the things that they're doing is like using the f double dash as your second derivative. All right, let's talk about the third one. And the third one, so gradient descent might have issues when it hits the flat regions, or what we call it plateaus. So suppose your function was having this behavior. So in this region, you have zero slope, right? Your derivative would be 0, but it doesn't show any local or global minimum for us, because actually the global minimum was here. So gradient descent would stuck here. So what can you do to avoid getting stuck in flat regions? Any thoughts?
Check for slopes on the side.
Check for slopes.
Check the points to the left and right are not also 0.
Check at j minus 1 and at j plus 1. If they are 0, then it's not a stopping condition.
That would be one case. Another easier one.
change scenarios?
It could help. It could be helpful, but suppose you had a huge plateau, like with whatever learning rate, you would just get stuck. Another.
Double derivative should be 0. If the double derivative is 0, then it's a flat rate.
Not always, but yeah, sometimes yes. Yeah.
What if you increase the learning rate?
Yeah, we had yeah. I mean, if the plateau was like long enough that you couldn't get past it, the easier, yeah.
You just start at a different point.
Yeah, I mean, it would be just easier to restart your iterations from a different point, randomly, right? You've started from this point and you got stuck here, so why not start from this point, and you find it here, right? You can iterate several times and see which way goes to your best, best point. So rerunning the algorithm using a different initial point, choosing a larger step size. So these might work in order to avoid you to get stuck in plateaus, or a combination of those, right? Okay. So let's wrap up this section with an interesting analysis over the differences in complexity between the least square optimization that you already know for the linear regression and the gradient descent. So if you would be still, because gradient descent is an iterative method and it's going to be applied on any convex functions, so you could be able to even use it on the case of linear regression, right? It's not just limits you just to use it for logistic regression, but also you can use it in linear regression or other convex function that you want to find the minimum. If you were to use it for linear regression, so adopting the in-sample error of W for linear regression would be like this. So you fill it in with the gradient descent. So your minimization function of D plus 1 dimensional space of R for your W would become, on the next step, you would have WK plus 1, your next iteration, as WK minus the rest of the in-sample error for your step size that you've taken on your iteration number K, right? So it would be, the K plus 1 would be K minus the step size with the error you had already with your step size. So if you simplify this, you're going to reach to this formula. Now, provided that your WK plus 1 in the case of linear regression was your WK minus this value in a case that your case, the number of iteration goes towards infinity, so you have many iterations, there's a very simple proof, you can check it in your textbook or online, that this formula converges to the good old formula of your least square. So it's going to be closer and closer to this function, W star of least square, LS. So you see that theoretically, if you pick good high number of iterations and your k goes towards infinity, you can apply gradient descent for linear regression as well. It's going to be sort of approximate the same least square function for you. But the point, the difference was, on the case of linear regression, you were to face a closed form, so you had you could calculate the absolute value with least square. But gradient descent is going to be an iterative method, so it's going to approximate you with certain number of iterations, right? So this is going to be the two differences. So now that we know both cases are going to converge to the same value, almost. So which one to choose in a case that we were trying to solve a linear regression? Questions? Okay. So given the two formulas, what are your thoughts on the complexity of these two algorithms? Like this one and a gradient descent one. This one. All right. Any thoughts on this?
Gradient descent is better in performance, like because we are doing order of n operations a lot of times, and since we are doing matrix multiplication in linear regression, we have an operation of order n cube.
Right. Yeah. Great. Yeah. So your colleague is right. Gradient descent is going to provide you with a number of iterations of order n, which is the first order, and it's going to be, and because it's in the first order, we don't care how much of n we are doing, how much of iteration we are doing. That's why GD, or gradient descent, has an order of nd, and n was the size of your, right? However, if you apply least square, because of the formula it has, x transpose, product of x transpose and x, and then you have, so let me just bring it up here. You had whereas x, because we were to compute the pseudo minus 1 pseudo inverse matrix, if you recall. So this portion gives you an order of d2 and d2, right? This portion gives you an order of nt, and also the final product is going to give you a d3 order. However, since in most of the machine learning cases our n is way bigger than d, because we had so many different input data set at different rows with respect to our features, like our D, like the column would be much smaller than the rows. So this would dominate, this ND2 D2 was dominating the other two because N was much, much higher. So the final order would be N D square, right? So you see that the gradient descent is having a much better order of complexity rather than least square. But least square gives us the closed form solution, which is the absolute solution, but GD has an approximated solution, right? So that's why in practice we see that exact solutions may be an overkill, because we could have just used some approximations to converge to our point in a reasonably smaller number of, a smaller scale of complexity using GD. So I would say this is the dominance. Let's see the dominant one among those three. All right, having said that, we almost concluded the linear section. So as a final recap, we talked about perceptron, we talked about linear regression, and we talked about logistic regression. So in the case of credit card problem, so the perceptron using our PLA or pocket algorithm would define as a classification to approve or deny a credit card given the historical data. In the case of linear regression, it would define us the exact W that the amount of credit should be in order to get passed. And in the case of logistic regression, it would give us a probability of a default that later on bank could use in order to approve or reject its own clients given that. And in order to solve those, so for the case of perceptron, we use PLA or pocket algorithm. For the linear regression, we use the sorting inverse to compute the square error. And also the logistic regression, we use gradient descent. And the in-sample error was calculating using cross entropy error, right? There are a couple of more slides that as a formalization of you have, the problem, the definition of design versus learning, which you already know. Design gives you a definite answer using mathematical or analytical solution. However, learning uses data to do that. So I'm just wrapping up and put this slide at the end of this section. You can have a look at it later on. Also, there are a couple of recap slides for all the formalizations of your linear problems, starting from the input, output, and also how you're going to define the task, how you're going to define your learning model, and the algorithm and loss function. So I'm going to put them all in the last couple of few slides of the lecture when I'm uploading it today. All right, so starting from next session, we're going to talk about stochastic gradient descent, and we go towards neural network after that. You have a good day, guys.